Hello 20-1 students. So today we're starting with chapter 9, looking at linear and quadratic inequalities. So again, you have your layout, for the unit of how you should be timing things. So you can have a look through that. We're going to jump right into lesson 9.1, where we're looking at linear inequalities in two variables. So it's a lot of big words, but basically what we're looking at is linear graphs, so graphs of straight lines, not parabolas, like not quadratic, and we have two variables in our equation. So that's going to be our y value and our x value. And instead of just having y is equal to, whatever our equation for our graph is, like we've looked at in the past, we're going to have inequalities. And so inequalities are basically where instead of an equal sign, we're going to have a greater than, like a less than or a greater than, or it could be like a less than or equal to, or a greater than or equal to sign. Okay, so we'll see all of those as we move through the lesson. Actually, you can kind of see them down here. These are the different versions that we could see. So just to kind of start out thinking about what are we looking at when we're looking at linear inequalities. Basically, in each of these graphs here, we have a line that is the graph of y being equal to x. So essentially, both of these lines are identical, and they are graphed by saying that for every y coordinate, we have the exact same value for the x coordinate. So it would be like, if x is 1, y is 1. If x is 2, y is 2. However, we notice that there's a difference between these two graphs because of where the graph is shaded in. And we haven't really looked at shading yet in graphs, but we can see that in this one where it says y is less than x, we have every point below the line shaded. And for y is greater than x, we have every point above the line shaded. And so basically all that's saying is we're looking at y being less than x, so all of these points in this shaded area would have coordinates in which the y coordinate is less than the x coordinate. So you could pick any point underneath this line and the y value for that point will be less than the x value for the same point. So for example, if we go, let's say on the y-axis and we choose negative, it's hard to see the numbers, but let's say -6 on the y-axis. So that's -6 for our y value. Well, because we're on the y-axis, our x value will be 0. And so if we think about the inequality there, what this is telling us and the shading is telling us is that this value should be less than that value, right? So we can fill in that inequality. And of course, that's true. -6 is less than 0. Okay, and you could go to any other point. If we go on the x-axis, for example, we could go to, say, +4 maybe for x. And because it's right on the axis, y would be 0. And again, we see that this is a true statement. 0 is less than 4. Okay, so basically when we're shading in a graph, all we're doing is we're filling in the area to demonstrate how the variables relate to each other, whether they're greater than or less than or equal to or more than one of those. So same thing over here, except for it's the opposite. Y is greater than x. So we have the area shaded above the graph because it's greater than. And every point in this shaded region should fill this inequality. So for example, if we were to go up on the y-axis here, we can see that the shaded points now are on the positive part of the y-axis. So let's say we pick any positive y value, let's say maybe 5. Well, because it's right on the y-axis, our x value for that would be 0. And we see that it is true. 5 is greater than 0, so our inequality is true. So all of the points in this shaded region are going to give us that same comparison of your x and y values. Okay. So just a little bit of a reminder here that the graph of a linear function is always going to be a straight line, which is pretty obvious, but it divides the Cartesian plane into two regions. So the Cartesian plane is just, our 4-quadrant graph, and when we draw any line anywhere in this, whether it's, more horizontal, more vertical, or on any kind of a diagonal, it basically divides this area into two areas. Or into two parts. And so the two regions of the graph are always going to represent the inequality. So essentially, if you're looking at greater than or less than, it's always going to fill in, you can represent that rather, I guess, by shading in that area. So here's the general rule of this. The line is represented by the equation, in this case, a generalized version would be ax plus by equals c. So that's our equation for our actual line. As soon as we change that equal sign, if we're looking for the graph to be greater than this value, we're going to be shading the above region. If it's less than, we're going to be shading the region below the line. Okay, and so we end up with 4 possibilities of how we would write that inequality, because there's less than or greater than, but there's also less than or equal to and greater than or equal to. So in these cases, which we haven't really looked at yet, basically that means spots on the line would also satisfy that inequality. So, if these would have been y is greater than or equal to, that means you could have picked a spot on the line, and the same thing would have been true for the values, right? The y value would have been greater than the y value or equal to it. Okay, so just a little bit of vocab before we start moving into kind of like some examples where we'll see a little bit of how this works, and usually that's where it starts to make more sense. So when we're talking about a solution for these graphs, we're basically just talking about an ordered pair. So we're talking about a point on the graph, so we always represent that with x first and then y. And it's a solution to a linear equality if the inequality is true when the values of x and y are substituted into the inequality. So essentially, like, this would have been a solution for this graph, right? You would have gone to y equals 5 and x equals 0, and basically, because it's in the shaded region and it is true when you put in the inequality, it's a solution to that graph. So essentially that means all of the points in this shaded area are solutions to that particular graph. Well, sorry. And there we go, right in the vocab. So maybe we should have been a little more clear with that. But basically, the solution is the actual points. The solution region is that shaded area where all the points inside of it will satisfy that inequality. Okay, so just a little bit of a distinction there between the two of those terms. Lastly, we have the boundary, and so this is just our actual line, right? So the graph that's dividing the plane into the two regions, which may or may not be part of the solution region. So remember, if your inequality is less than or equal to or greater than or equal to, it is part of the solution. Okay, so it's included in the solution region. And when our line is part of the solution area, we draw it as a solid line. So basically just the way you've drawn all of your graphs. So the only thing that's going to be different is if our inequality is just less than or greater than, so there's no equal sign underneath them, that means that our line is not part of the solution region. So that means that it wouldn't be true for the actual points on the line. And when that's the case, then we draw our line with a dashed line. Okay, so this is different than what we've done so far. We've never used, dashed lines to draw our graphs. So we change how we draw the graph a little bit if the graph itself, like if the line itself is not part of the solution. And that means that all of the solutions would have to be greater than or less than, but not on the line. Lastly, one of the things that we want to do, and kind of what we were actually doing in the previous page, is, we would just pick points in this, what we saw as the shaded area or the solution region, and we would just pick a point and plug it in and see, does it match what we're expecting based on our inequality? And that's called a test point. So it's where you basically just pick any kind of point within either the shaded region or the not shaded region to determine whether or not it satisfies the inequality. So the only thing that you want to make sure with your test points is you want to make sure that they're not on the boundary. Okay, so don't choose a point on the line. Choose one that's clearly in the shaded region or in the non-shaded region. If it's in the shaded region, when you put the points in, just like we saw in these ones, it should actually be true. So like 5 is greater than 0. If you were to pick a point in the unshaded region, you just have to know that your test point should not be true. So like say if we picked, positive 5 on the x. So let's say positive 5 on the x. And because that's on the axis, our y value for that would be 0. And your inequality stays the same way, right? So you still have your y and then your inequality and your x. 0 is not greater than 5. So if you pick a region, like a test point not in the solution region, you should expect it to not be true. And that still validates your inequality, right? Because it's saying, yes, you shaded the right part, because clearly the points that are not shaded are not part of the solution region. Okay, so lots of stuff coming at you right to begin with, but we'll get into some examples here really quickly, and hopefully things will kind of become more clear. Now I do want to just point out really quickly some options you have for graphing your inequalities that are just going to make it a little bit easier if you kind of know the general ideas. So the first thing is, it's usually easier if you're working with a linear equation, if you can make sure that it's written in slope-intercept form. So basically, like, whatever you're given as an equation, you want to rearrange it so that y is all on its own, and then you're left with, the kind of format of, possibly a coefficient with an x value and then another number, or maybe no number, which would mean that you have a y-intercept of 0. So just throwing my pen around here. So just remembering m always represents your slope and b always represents your y-intercept. Okay. Also keep in mind, because like when you write this, what you're actually going to end up working with is an inequality here, right? Because we're looking at shading above or below. So if you end up changing like the positives and negatives, your inequality sign is going to switch direction. Now, personally, the way that I do it and the way that I'll show it to you guys as we work through this, I always make sure that I set it up so that I don't have to worry about switching the direction. So I wouldn't worry too much about that, but just be aware that if you switch the negatives, you do have to make sure you change the direction of the inequality. And then last thing is you want to graph and shade the region based on the following guidelines. So if you solve for your equation, your inequality, and you end up with y being less than, your formula for the line, then basically what you're going to have is it's just less than, not less than or equal to, so that means you need a dashed line, right? And then, so I'm just going to draw in kind of like a dashed line here, and then that means that because it's y is less than, you're going to shade below the line. So I would say, like, when you guys first start out trying these kind of questions on your own, you might want to use this kind of as a little bit of a cheat sheet to kind of remember how things go, because it just makes things a little bit easier to start out with. And then as you become more comfortable and you kind of know how things work, you probably won't need this anymore, but it's handy when you first get started. So the next one is y is less than or equal to your equation for the line. So in this case, your line is going to be a solid line because we have that less than or equal to. One of the ways that I always remember that is there's more kind of like lines in the less than or equal than there is in just the less than. So I always think of like that equal sign as filling in the gaps between these spaces so that I can remember that this one is dashed and then there's more lines in the less than or equal to, so I know I want a solid line. And again, because it's less than or equal to, I'm going to shade below the graph. So all of these points are going to be true for this inequality. And then, you know, basically just the opposite for greater than is still going to be a dashed line because it's not greater than or equal to. And because it's greater than, you're going to shade above. Okay, and then greater than or equal, same thing, except for you're going to have a solid line in that one. And then you're just going to shade above like that. Okay. So that's kind of your first option. The other option would be to just graph your x and y intercepts. So basically, if whatever you have for your equation, not necessarily changing it into this form, instead you would just plug into whatever format of the equation you have. You would plug in 0 for your y value, and that will help you to solve for what your x would be. So that will give you your your y intercepts, and then for your x intercepts, you're setting x to 0. No, sorry, the other way around. Set y to 0 to find your x-intercept and set x to 0 to find your y-intercept. So basically you're just substituting in 0 for your y or your x values, and that will give you your opposite value, and then you can just graph from there because you'll have a few points to work from. And once you have those intercepts too, you can also solve for your slope, and then you can plot more points if you need to. Once you have that done, you're again going to do the same thing. You're going to use a test point from each region to determine which section contains the solution. So kind of like what we did in the first two graphs there on the previous page. And then you're just going to shade the appropriate region based on those test points. Okay, so hopefully that wasn't super overwhelming for you guys, because now we're going to try some examples, and hopefully that'll help to make it a little bit more clear of what we are trying to do here. So, in this first example, what I want to do is, so we have 4x plus 2y is greater than or equal to 10. So for this one, I'm going to use option 1 that we just talked about, which is that I'm going to try to put this into like y equals mx plus b form. All that means that I'm going to do is I'm going to isolate my y value. Okay, so my first step is to isolate y, so that means I'm going to have, I'll just write out the first one, 4x plus 2y is greater than or equal to 10. And so the first thing I want to do is subtract off 4x, and that's going to leave me with 2y on the left side being greater than or equal to 10 minus 4x. And then I just want to divide away that 2, so I'm isolating my y variable. So that's going to give me y is greater than or equal to 10 divided by 2 is 5, minus 4 divided by 2 is 2x. Great. Okay, so this is a little bit of a variation on, like, our linear formula is y equals mx plus b. It doesn't matter if it's in that order though, right? So our solo kind of like number value here is going to be our y-intercept. So that means our graph is going to cross the y-intercept at y is equal to 5. And then our slope is the m value, right? So in this case, that's -2. So basically that means from the point that we have at the y-intercept, we want to go down 1, 2, and over 1. So remember, with our slope, we always think of it as a fraction. So if you have a whole number value, so for example, like here we have -2, if we write that as a fraction, it's 1. And remember that basically what we're saying there with slope is rise over run. Okay, so we go down 2 for our rise and over 1 for our run. So we can do that, a few more times. 1, 2, 1, 1, 2, 1, 1, 2, 1, 1, 2, 1. Whatever, good enough. And also, if you want to go in the reverse too, like all you need to know is if you have a negative value that your graph should be sloped, so that if you're going from left to right, it's going downwards. If it's a positive value, if you go from left to right, the line should be ascending. So basically with this one, if you want to continue your line backwards from where you were, you would just keep going like, let's see, our run is still 1, so over 1, up 2, over 1, up 2. So there's our line. Let me just grab a ruler and I'll connect those lines. Okay, so there's our line, and what we're trying to do is determine if point 1, 3 is part of the solution. So let's see, 1 on the x-axis and 1, 2, 3 on the y-axis. Oh wow, they're really trying to make that tricky for us because it's right on the line. Is that right? Just see here. So we're at 4 and then 3, 1. Yeah, that is right. Okay, so maybe let's just try and figure out if we want to shade above or below the graph, and then we can kind of determine, first of all, what's the solution area, and then we can determine if 1, 3 is part of the solution. So let's just pick a random point, let's say above the graph. It doesn't really matter. Actually, let's do below because we have a nice easy, usually what I like to do is, if you can, I pick always the easiest, which is 0, 0. So essentially what I would do there is I just want to plug those values in for x and y and see if the inequality is true when I put those in. So that would mean I would put in for x is 0, so 4 multiplied by 0, plus 2 multiplied by my y value there would be 0 as well, greater than or equal to 10. So 4 times 0 is 0 plus 0 greater than or equal to 10. So basically, is 0 greater than or equal to 10? Well, 0, whoops, and I'm leaving the 1 out, which is going to make it confusing. So 0 clearly is not greater than 10. So that means this section below the graph is not true, right? So this inequality would not be true for any points under the graph. So that means we want to shade the top part, so above our graph. If we want to figure out if 1, 3 is part of the solution, I mean, we already have a greater than or equal to, so we would assume that it is because it's on the point of the graph, but we can substitute it in as well and just double check. So basically 1 would be, remember that it's always x, y, so we would put in, to check for that point, 4 times by x, which is 1, plus 2 times by y, which is 3, is greater than or equal to 10. So 4 times 1 is 4, plus 2 times 3 is 6, greater than or equal to 10. 6 and 4 is 10, which is greater than or equal to 10. And of course it's equal to 10 because it's right on the line. And so we see that our inequality is accurate, and that, I mean, the shading, we had to determine a different point to solve for that. So, and that's a good takeaway from this example, is that if you are asked to find a point on the line, you can't use that to determine which part of the solution you need to shade. So then you do always have to do a separate test point in like the area that's clearly above or below the line to determine whether or not it's accurate. All right, next one here, kind of similar, 5x minus 20y is less than 0, and they're asking how can we verify our solution. So for this graph, I actually wanted to show you guys the second possibility of how to do these types of questions, but it actually ends up so that you don't end up with two different points if you find your x and y intercepts, because they're both 0, 0, so it doesn't really work for this one. So we're actually going to follow the same method as we just did in the previous one. So again, we just want to isolate y in our first step. So 5x minus 20y is less than 0. So we want to get that y on its own. So let's actually, so this is kind of where I can talk about switching the inequality sign like we talked about kind of when we were looking at that. If you were to move your 5x over, you would have a negative value in front of this y, which would mean you would need to divide out a negative value, which then you end up having to worry about the inequality sign. This is how I do it so that I don't have to worry about that. Basically, I would just say I don't want to worry about a negative value on the variable that I'm trying to isolate. So instead of subtracting 5x to move it away, I'm just going to move the y value to the other side of the inequality because it functions the same way. So basically, I would say plus 20y plus 20y. And then that's going to be, let's see, 5x is less than 0 plus 20y, which is 20y. And then I just want to divide away my 5. So that's going to leave me with x is less than, wait, sorry you guys, I need to divide away the 20. I am not thinking clearly. Okay, so I want to divide away the 20 because I'm trying to isolate my y. So 20 divided by 20 is going to leave me with y, and 5 over 20 does not properly reduce, like it doesn't divide to a whole number, but it reduces to a fraction. So 5 goes into 5 one time, and it goes into 20 4 times. So we're left with 1/4 x on this side. Okay, and so basically we're saying 1/4 x is greater than y. So again, if you are trying to think about your slope-intercept form like we looked at up here, m, so the value that's in front of x is your slope. So basically this means we're going to be going up 1 and over 4 for every kind of unit of slope. And then we don't have any number value being added or subtracted from that. So that means that our y-intercept is at 0. So that means that the line is going to cross the y-intercept when x is equal to 0. From that point, we're going to go up 1 and over 4. So up 1 over 1, 2, 3, 4. Up 1 over 1, 2, 3, 4. And again, like we can also work backwards. We're going to go down 1 and back 1, 2, 3, 4. Down 1 and back 1, 2, 3, 4. Okay, and then we just want to, I'm misplacing my ruler here. So we just want to shade in the line there. Oops. That's working out really well. Okay. All right, so there's my line, and then we just want to figure out where we would shade. So because we're not given a specific point to test, we want to just pick our own test point. Now my favorite 0, 0 is taken away, so I don't know, let's try maybe up here. Let's try 2, 2. So I'm going to test 2, 2, and so that means it's nice sometimes if you can pick values that are the same, because then you don't have to worry if you accidentally confuse the x and the y. So I'm going to do 5 times by my x value is 2 minus 20 times by my y value of 2, which is less than 0. So 5 times 2 is 10, minus 20 times 2 is 40, which is less than 0. 10 minus 40 is negative 30. And so if we look at our inequality, it's true that negative 30 is less than 0. So that means we're going to shade this region above our graph. And, you know, it asks us how we can verify our solution. Basically, we're verifying our solution by substituting in values from the region we've shaded and determining whether or not they result in a true inequality, which we did end up with here, right? Because we said negative 30 is less than 0, so that's basically how we're verifying it. Can't really think of anything else I need to say for that one. So if you guys want now, you can pause the video and give this one a try yourself. So there's a similar kind of a setup here, and you need to determine if negative 2, 4 is part of the solution. If you want to see the full worked solution, you can go to page 466 of the textbook to see that. Okay, so for the next question, we just have 2 questions left here. I know it's a bit of a longer lesson, but just bear with me. So we're just going to write an inequality to represent this graph. So basically what we need to do is we need to figure out what is the equation of this line, and then because of the shading and the fact the line is solid, we can turn that equation into an inequality. So probably the trickiest part is writing our equation. So just keep in mind we want to follow the format y equals mx plus b. So essentially what we want to do is figure out what our y-intercept is. Now I kind of maybe didn't pick the very best graph here for this because it didn't end up quite connecting. But essentially what I wanted to show there is that the intercept, the y-intercept, is at negative 10. So my value for b is going to be negative 10. And in terms of slope, basically what I would usually do is just look along the line from my y-intercept. Where is the first point where this graph like intersects, you know, nicely with 2 lines? So I would say it's here. So that would mean we would go back 1 and up 1, 2. And then we can always see if that holds true. So if we go back 1 and up 1, 2, back 1 and up 1, 2, we find that we do keep hitting like an intersection of 2 whole numbers. So that means our slope is, if we go from left to right, we're going downwards. So we know we have a negative slope. So our value for m is going to be negative. And you know, sometimes it's hard mentally just to like think about going backwards. So what you can always do too is pick like one of these intersections and say, okay, what's happening for my rise? I'm going down 2, which is my negative 2, and then I'm going over 1. So it's negative 2 over 1, which is just negative 2. And then, you know, just x always just stays the same. So y is equal to negative 2x minus 10. So that's our equation for the line. Now we want to think about the fact we have a solid line. So that means we're going to be working with either greater than or equal to or less than or equal to. So all we need to do is figure out which one of these. We're shaded above the line, so it's going to be greater than or equal to. If you wanted to, you could always try a test point to make sure. But as of right now, I would say we're looking at y is greater than or equal to, because we're above the line and it's solid, so it has to have the equal to, negative 2x minus 10. Okay, and like I said, like if you want to choose a test point in there, you can just verify. So like 0, 0 is in the shaded region. So we could substitute 0 for y, greater than or equal to negative 2 times by 0 minus 10. So that would be 0 is greater than or equal to 0 minus 10, which is negative 10. And it's true that 0 is greater than negative 10. So we know that we wrote the correct inequality for the graph. Okay. So again, if you want to pause the video, there's a couple for you to try out here on your own. And you can check the filled in notes for the solution to those. Oh, actually, I'm looking at the filled in notes and I don't have those. So maybe I'll work those really quickly and I'll put them into the video. All right, guys, so I put the solutions in here so you can check them against there. In this one, I don't know why, but the Cartesian plane didn't end up showing up, but this should have been kind of like, I guess I should have drawn that in while I was doing the solution, but this should have been your x-axis right there. Okay, so that's how I came up with the +4 for the y-intercept. Okay, I know that those, the graphs are a little bit not super clear, so if you came up with something like moderately different for the slope, that's okay. So last type of a question is where you have a word problem where you're given the variables and information about them, but not the equation itself. So suppose you're constructing a tabletop using aluminum and glass. The most you can spend on materials is $50. Laminated safety glass costs $60 per meter squared, and aluminum costs $1.75 per foot. You can choose the dimensions of the table and the amount of each material used. Find all possible combinations of materials sufficient to make the tabletop. So basically with this, you're looking at a linear relationship where as the amount of one material increases, the other decreases, and vice versa. So the first thing you want to do with problems like this is identify your variables and just assign them, like assign one of these values to a variable. So basically what we're working with is glass and aluminum. So let's say that X is our amount of glass, and let's say Y is our amount of aluminum. Okay, so basically we want to figure out what combinations or what possibilities, if X is one variable or like one amount, how much would Y be? So when we're thinking about our inequality, basically what we would have is we want to relate it to our total, like the thing we're defining everything against is how much money we can spend. So we have $50 to spend, and so basically that means we need to spend our amount of our materials times by their price needs to be less than or equal to the 50, right? So whatever we have over here for our materials multiplied by their cost, it needs to be less than or equal to the $50 that we have. So basically what we would have is the glass costs $60 per meter squared. So 60 is our price, and we would times it by however much glass we get. So that'd be X. Plus we need however much aluminum we have, and aluminum is $1.75, so 1.75 times by however much aluminum we have, so Y. So our inequality is the amount of glass times by its price plus the amount of aluminum times by its price, and together those need to add up to being less than or equal to the $50 that we have to spend. So once we have our inequality set up, we need to rewrite it in slope-intercept form, just like we did for the other ones, so that we can draw it as a graph. So basically, we want to isolate Y. So the first thing I would do is subtract that 60x off. So I'm just going to do that, like in one step here. I'm going to do 50 minus 60x is going to be greater than or equal to, so I've subtracted this 60x to that side, so I'm just left with the 1.75y, and then of course I want to divide away that 1.75 from both sides. So when I do that, I'm left with 50 divided by 1.75. I'm just going to, like I just did it in my calculator and solved for a numerical value. So I got 28.6, which, is kind of like a rounded decimal, but 28.6 minus 60 divided by 1.75 was 34.3. Again, kind of rounding it off to the nearest tenth. And that's going to be greater than or equal to 1.75 divides into itself, so it cancels, and we're left with Y. So now when I wanted to graph this, I think I did let's see, 5, 10, 15, 20, 25, 30, 35. So I set this in 5s. And basically, oh, whoops, I forgot to put in my x there. That's pretty important. Maybe I'll just bump over that inequality so we can see that a little more clearly. Okay, so 34.3 is going to be 5, 10, 15, 20, 25, 30, 35. So, 34.3 is going to be like just right below there if this is 35 here. So that's my y-intercept. Oh, shoot, you guys. Sorry. Totally wasn't following that properly. My y-intercept is just the numerical value, so it's not going to be this point at all. It's going to be 5, 10, 15, 20, 25, 30. So be kind of like just a little over halfway between those two. I mean, we don't have to be too careful. And then our slope is kind of a weird one, right? Because it's negative 34.3. All that tells us is that from here, we would go down 34.3 and over 1. So I think that brought me down to like, actually, let me just do that in my calculator real quick. So that brings me down to negative 5.7. So 5 and like a tiny little bit. And we'd be over 1. So we'd be at, let's set this x-axis is just going to be like 1, 2, 3 normal kind of numbering, whereas our y one was going up by 5s. So that's kind of our general idea of the slope, and I'm not even going to really worry about putting in more than that. Two dots is enough for that. Okay, so that's going to be my line. Now I just need to think about what's going on here. So it's greater than or equal to, so good thing I drew a solid line in there. And then greater than or equal to, remember that when you're interpreting this, we need to interpret from the y perspective. So I know this is kind of in reverse because we moved the y to the other side. So actually y is less than or equal to. So that means we're going to be shading underneath this graph. And you can always do a test point to be sure. So another thing to just be aware of before we work with the test point is because just keeping in mind what our variables are, like x and y. So this was our amount of aluminum was our y-axis, and our amount of glass was our x-axis. So when you're graphing something that's related to a practical, like a word problem that relates to a real life situation, you want to make sure that you're shading and even maybe drawing your line in a way that it represents the real life situation. So if y is our amount of aluminum and x is our amount of glass, we can't actually have a value that's going to go into the negatives for either one of those, right? We can't have a negative amount of glass or a negative amount of aluminum. So that means our test area or our solution area is actually only below the graph but above the axes, right? So it can't go into the negatives. So now if we want to pick a test point, I don't know, whatever, we can go, like let's say 0.5, and we would go 5, 10. No, actually, let's just make sure we're really sure. So 0.5, and for sure that in this region we would have, for the 0.5x, we would have 5 on the y. So if we were to go 0.5, whoops, so I close off the bracket, 0.5 and 5 on the y. So if we substitute those values in to our equation, or rather our inequality, we have 50 is greater than or equal to 60x. Sorry guys, you can tell I'm getting to the end of a long lesson here. 60 times by 0.5 plus 1.75y. And again, I have put in a variable there when I meant to put in a number. Okay, so that would be 50 is greater than or equal to 60 times 0.5 is 30. 1.75 times 5 is 8. 38.75, so we have 38.75, and so we see it's true, 50 is greater than 38.75. So if we were to talk about this solution region in the context of the question, basically what we would say is, you know, any point in this shaded area can represent the amount of glass and aluminum that together would satisfy you know, the inequality where you're spending less than or equal to $50. So for example, if we choose 0.5, 5, that means we have 0.5 was our x value. So that means we would have 0.5, and our glass was being measured in meters squared. So we would have a ½ meter squared of glass. Sorry guys, I'm working outside of my camera zone there. A ½ meter squared of glass, and for the aluminum we would have 5, and our units there are feet, 5 feet of aluminum. And you would basically just say for a word problem like ½ meter squared of glass and 5 feet of aluminum is one possible combination that would allow you to build a table for less than or equal to $50. And we ended up with 38.75, so you would have for sure less than $50. That's the actual amount you would spend. So you could even write that in your answer. If you used a ½ meter squared of glass and 5 feet of aluminum, you would spend $38.75, which would be less than your budget of $50. Of course, the values as you get closer and closer to the line, or if you're on the line, you'll be spending $50, right? So, but as you get closer to the line, you're spending closer and closer to $50. Okay, so that's everything for today, guys. Thanks for sticking with me for such a long lesson. Now, reward yourself by going to the textbook and trying some of these practice problems, and hopefully you will ace them all. And I will see you in the next lesson when we start looking at graphing quadratics. So things are going to get slightly more complex there. So I will see you then.